the first thing about this is we're going to discuss matrices, and so if again, I'm assuming that people who are going to watch this maybe have little to no experience with linear algebra, nor are they familiar with the like syntax that's used in quantum theory. So we're going to assume that that's the case, and we're going to start from scratch. I haven't done this stuff in a while, so it'll be good for me to go over as well. Um, like I do some like vector stuff, but not a ton of matrix stuff. So anyway, here we go. So matrix A. I don't like this. Oh, maybe this is fine. Um, 1, 3, A 1. So number of columns. I don't know how many written out. We'll write a few out. Like so. Right? And then, there's everything in between. Oh, I didn't close. Little tight in there, but that's okay. So, this is the like general form of a matrix, and typically the A here is like in bold or something like that. It really depends, but it's hard to write bold in here. Like I could switch the pen, but that's kind of a pain in the butt, right? So we have m rows and n columns. Um, a lot of, I guess, like you mentioned that in books and stuff, sometimes there's no comma separators between the the types. You should be able to see pointing at. This is so nice. So sometimes there's no comma here, but he mentions like it's kind of difficult to figure out what like um, a if we wrote this, what would that mean? Right? Like what's 131? Who knows? Could be 13.1, could be 131. Unsure. So that's what the comma is for, just to separate their positions. Um, when m equals n, that's called square. Some of this stuff you may already know, but again, I'm pretending that we know nothing and we've never done this before. Usually we'll denote matrices with obviously like capital letters like this, and vectors will be lowercase letters. So a vector in this case, like A, we could also write it as a cat, like that. So this is a syntax called cat notation. Cat. Um, and this one is a cat. A bra would look like this, and that means something different, which we'll talk about in a little bit. But that's what it is. And then like a vector could be written like 1, 2, right? So we assume that standard vectors are column vectors and written in this equation. Sometimes in an equation, we want to point out explicitly which quantity is a matrix and which one is a vector. So for matrices, we might use like a box around it and then maybe a like that. So this would be like vector. This would be matrix. Not necessarily a square matrix, but a matrix. By the way, if you have any trouble hearing me, just let me know. I don't want to, if I'm quiet, I need to know. Okay. Um, let's see here. So there's a matrix. Uh, we now we're going to start talking about other things. So let's talk about a trace. Trace. in the book will be written TRA, which is the sum along the diagonal of the matrix. So the diagonal is like A11, A22, A33 to AMN. So you can write that as the sum from I equals 1, N, A, in this case, and N is just like the dimension. Okay, and then we have matrix addition. This, and so for matrix addition, like this is element-wise addition, so we would write like B equals A plus B. Again, we could put squares around them if you wanted to explicitly state that they're matrix. But this is element-wise addition, so you could write it with like the indices as Bij A J plus J. We could also write it in like a summation notation or something, but hopefully that's pretty clear. Just like a tiny example. 4 plus 6, 0, 1. So we just do this across, so it's just 7, 5, 2, 3. Like that. So it's just element wise. So right, this one plus this one plus that one plus that one plus that one. Hopefully you saw my marker the whole time, which is, the marker is so cool. I didn't know that we had the marker. You don't see the marker on my screen, so I have to like guess how far it is away. So that's like a very basic matrix addition. And so what we're going to do now is, because I've not used Hasktorch all that much, we're going to try and write this in Hasktorch. So let's do that. So I think I have this file homing pigeon here, and it has like some stuff in here. So I want to move this to like source example regression Haskell or something. So module example regression where, and then we're gonna grab like all of this and we're gonna stick it over here like so. Okay, and I think that in app main we use this homing pigeon thing, so I think it ends up being, what did I call it? Example regression. We don't use this either, or this, or this. So, okay. So we should still be able to COBOL build, I think. Sorry. We need to run make build because we have HPAC going. And then it should be okay. Oh, I didn't include. There's a when in here too, which we need. Okay, and then this I want to remove. And then I would also like to fix this because I'm not going to use hedgehog. So I think we'll just delete all of this and this. And for now, just put pure that there, like so. Okay. So we should be good now. What is going on? That's weird. Okay. Nice. So now in homing Pigeon, we need to import torch, and we're gonna write like two matrices. So we're gonna just we're just gonna use like C equals AB. So I think A you just can write is like a tensor. There may be more stuff on Hasktorch. Some more. Documentation or something. Getting started, maybe. Learn more. Join the community. Getting started. Here we go. Docs. Tensors. Okay. So this is a tensor of zeros. We want a tensor of, floats is fine, I guess. So we're going to say that A is equal to, we need a list of lists, which I assume is going to be 1, 2, 3, 4. And then we're going to say that this is going to be list of float. And then we say as tensor. Okay, can't put a $sign there. That's fine. And then I guess this is okay. I don't know what this does. Like, it seems to me it takes some tensor-like. Interesting. Okay. So we're specializing it to list of float. So we might be able to say at. I want to see if we can use type applications. Looks like yes. So now we have, I guess I could use like capital A to avoid confusion, right, of vectors. But these might not be, these aren't valid, I don't think. Oops. So we'll have to think of a way to like write these things, I guess. Party of 59. Raphael, hey, how's it going? Cool. How's it going? How was your stream? What were you working on? So while you're writing that up, I'll explain kind of what's going on right now. So I have in front of me two things. I have a book that's Quantum Theory for Chemical Application, and I have a Remarkable. Okay, so the Remarkable is basically being screencast in front of you so that I can like write on it and like point things out like that. And that way I can like do linear algebra on the stream. I haven't done this stuff in a while, so we're doing a primer and just like getting everyone hopefully at the same on the same page. And then simultaneously we're messing around with Hasktorch, which is Hasktorch here or here, and trying to like learn how to use Hasktorch to do linear algebra so that we can like solve problems in quantum chemistry. All right. I'm porting a C++ Maya plugin to Jai, John Blow's new language. Been going well. Cool. Still private beta. I think that I watched your stream at one point. I can't recall now. I may even follow you. I'm not sure. But I should follow you, and I probably will. So right now we're trying to do Elementwise Addition, and I don't know if it's like as simple as writing A plus B. I mean, if it compiles, it works, right? So let's see if like it actually works. So not stack. We need cabal make REPL. Maybe just cabal REPL. Lunchtime for me. See you later. Take it easy. How is the performance of Haskell? In like compared to what, or in what sense? Like for memory managed like language, it's pretty fast to me. When it's not fast, it can be pretty unclear why it's not fast, but that's usually not an issue for me. Also, great name, by the way, nanometer. It fits very good with what we're working on, or what we'll be working on. So we need to import homing pigeon probably, and then just like look at C. Oh, so it did do okay, so libtorch is implemented in C++. Hasktorch is just a binding. So yeah, that's 100% true. Yeah, Valigo, nice. You just wrap your IO modad into the fast modad and everything goes faster. Exactly. 100%. Yeah, so this is pretty similar to NumPy, but this did actually do what we expect. So this is, in fact, Elementwise wise addition. I just didn't put the right numbers in here. So 6, 0, 2, and I might have to put this in quotes. I can't recall. And if we reload, we can look at C, and there you go, 7253. It's similar to NumPy, but actually does what we expect. I'm not sure that that's necessarily true, but in this particular case, it does do what we expect. I think that I can't even remember what plus does in NumPy, if it does element-wise or like, I guess multiplication is the part where you're unsure if it's going to do element-wise or like actual matrix multiplication. So we'll see. But anyway, that was pretty easy to like write a few tensors and add them together. So cool, we did that. In this particular case, yeah, but like literally everything's going to be in libtorch. So I would be surprised if Haskell's ever going to slow us down in this particular case. If we started writing stuff in like more stuff in Haskell, then it would be a different story. But this is pretty much just a libtorch wrapper in our use case. Yeah. Okay. So I wonder if we can also take a trace real quick. So if we tensor d, is there a trace function? Looks like there's a trace function. Oh, but it takes a lot of stuff. What? Why does it take all of these things? Okay. So this is in torch.script, but it takes a lot of stuff. I don't exactly know why that is. So yeah, we can also put this on the GPU. That's true. Our current version does not work on the GPU, but it could. So one thing that is going to be a problem here is I probably could just use PyTorch's documentation. PyTorch docs. And then we'll just look for trace. Because I bet you oh, well, okay. So this just comes from Torch. But there's like seemingly multiple traces because the one that I had was from torch script. Trace. What else comes up? Torch script. So what's this? Sorry, there's going to be times like this where like I don't know what something is called because there's like no way for me to know what it's called as far as I know. So this takes a module name, a function name. This does not seem like the thing we're supposed to be using, does it? Okay. Yeah, like I see this here. No. So a trace is this piece of math right here. So a trace should take basically the sum along the diagonal. So if we ran the trace on C, we would just do 7 plus 3, and it would be 10, obviously. And that's kind of what I'm trying to produce. Traces are pretty useful, but I find this very weird. Trace as graph. I'm gonna have to ask about this because I'm like kind of surprised by this. Like I don't really understand what this trace is supposed to be. I would have guessed that it should be like this. So it did seem like there was some other stuff in here that had trace in it. Oh, also we're in one like there's some other stuff here. There's like script, torch script. Tracer. Yeah, like this is this trace function. There are some edge cases where the trace of given will not represent the underlying code. Okay, so this trace is different than like the trace I'm expecting. That's why this is confusing. So this is this thing. It takes like whatever these are. But that's not what we're looking for. We're looking for like the actual matrix trace, um, which could be straight up in like tensor or something. So let's see if we can find that real quick. Oops. It would be probably here. Torch internal. Doesn't look like it's there. Tensor. Trace. This is like literally just. I don't think there are tensor operations in here. Oh, there's too dense, too sparse, too CUDA. Anyway, the point is it's not the thing I was expecting, which is fine. Like we can't do a trace, so I'm just gonna put a question. How do we get matrix trace? And we'll continue reading. So let me put this back into a configuration that works, and we'll keep writing. Okay, so multiplication with a number, lambda. You'll like lambdas. I can move this down too. So if you multiplication with scalar, for example, like C equals lambda A, which is just Cij equals lambda Aij. I understand that my commas sometimes look like the J, but that's just like how I end up writing. And I presume that we can just do that like really easily here by saying like D is tensor and then D equals A times, I don't know, 2. And I would guess that this just builds, make build. Seems to work. We can also just make REPL down here. Sorry, I keep saying make REPL, but I don't mean that. There should be enough space down here for you to read this. But yeah, that's just... Is that what we expected to be? Oh, it was A times 2, so yes. 2, 4, 6, 8. Perfect. So that's multiplication with a scalar. Okay, and then matrix multiplication is the next part. So that is basically C equals AB, which written out is Cij. You can't really write that out with just the indices. You're going to write Cij equals sum of k, and then Aik Bkj, like so. And I'm going to assume that we can also do... We'll do this one by hand as well. I think there's an example in here. Oh yeah, there is. So perfect. We'll look at this. So E equals A times B. And also let's look at F B times A. And then down here, we can reload, and then we can do E and F. Okay, so this is actually the element-wise. So, okay. So, the operator times is element-wise as well, which is good. Like, I would say that that's actually a good thing. You can re-express trace from other operations. Probably, but I don't know the operations that I would use at the moment. Like, there's probably a function that we could use, like diag. Actually, let's see if we can find that one, because I bet you that one exists. So I don't really want this. So tensor times tensor is element-wise as well. What we want is probably matmul AB. and we want F to be matmul BA, and then reload this, and E and F. There we go. So I think that's the right answer. Let's see if we can find like a diagonal. Diag. Yep. So we probably can just do matrix trace like TR equals diag. Oh, what's diag? What's this type? Okay, so the argument diagonal controls which diagonal to consider. The main, I don't know what the above the main diagonal, I guess means like, here, let me draw it. So if we had a matrix like 1, 2, 3, this right here would be, I guess, the main diagonal, and then 4 and 6 would be the what was it called? Sorry, I got too many things on my desk right now. Above. And let's see if we can like actually get that to work. So I'm going to guess that this is just a 0, and then our tensor will be A. Okay, so diag is like an actual type. So diag. Oh, it takes a number. So it's probably like diag 0. And that should produce a one-dimensional tensor of 1, 4, which is the diagonal 1, 4. And get out can get out. That's kind of a funny name. And then in front of this, we could also just write probably sum. But this is the wrong sum. So we need to figure out what that's called in here. Abacus. No, acubus. I don't know why I wanted to call you abacus, but that's what came to mind. There's probably a sum in here, but we need to figure out how to get specifically that one. Maybe if we write literally torch.sum. Perhaps you meant sub, G sub, dim. Maybe there's something in here about like adding. I just don't know what this is called. Sum TS. That's like an internal one. Sum all. Oh, so this produces a tensor. Let's see if this is the right thing. So it should be 5. And it is. One thing I want to know is how do I pull out like a single value from this thing? Like, how do I get the value back out as a, like, the thing that I want? This is weird format. I could probably fix that. I mean, I guess we don't need to get the value back out, but I was just kind of curious how you do that. I don't remember what that is called in Torch. So let's look that up. So Torch or PyTorch get value out of tensor. How can I get the value of a tensor? Item. So let's see if there's item in here. This is going to be a bit like this sometimes. Like I don't really have any option otherwise. Maybe it's just get item, or maybe it's just item. Let's just try item. So if I do item, okay, so that doesn't exist. How about get item? Okay, so get item is a thing. Data set. That doesn't look like what I want. Kind of unfortunate. So, okay, so get item has to do with data sets, which is like, that seems reasonable. Oh, good idea. I can probably just do that. But again, that kind of isn't really what I want to do. Whatever. Let's just leave it as a tensor. It's fine. Like, it's really fine. I don't need to do this. But this would be a trace. And then I want to check the above diagonal thing because I've never done that before. So let's try and create a new tensor. And also let's call this like trace. Trace is going to take a tensor and return a tensor, and it's just going to be that. And then we're going to say trace A is going to take a tensor and return a tensor. Trace A is sum all dot diag 1, seemingly. If we look at this, wherever this went, whoops. Trace. Torch trace. Wait, what was I looking at? I thought it was this one. I don't remember what I was looking at. Oh, it's not this. It's diag. Right. Sorry. I'm being a goofus. Okay, so we were looking at diag. And then if it's greater than 0, it's above the main diagonal. So if we give this thing a 3-dimensional tensor, it should give us like hopefully the right thing is the idea. So G is going to be as tensor at 3-dimensional floating point. I wonder if I should just make a type alias for like 3-dimensional, 2-dimensional, etc., so that I don't have to like write this. But basically what this is doing for people who aren't familiar with Haskell is it's doing a type specification for what the first parametric type is. Sorry, polymorphic type is. So now I know that I have to give this thing a list of lists, and Oh, actually, it's not even this. It's just a list of lists. So that's wrong in the first place. But we'll just do 1, 2, 3, 4, 5, 6, and 7, 7, 8, 9, like so. And now if we reload this and look at G, it's that matrix. And so if we do the upper diagonal of G, so trace A, G, we should get 8 because it's going to add 6 and 2. If we just do trace G, homing pigeon, actually, like, we don't even want this. I don't even know what that thing does. So we're just going to hide it straight up like so. And then that way we don't have to like worry about this. And now we should just be able to do trace G. I just hit it. Maybe I can't make build. It looks like I already have homing pigeon, so I should have a trace G. Okay, I don't have that. So import homing pigeon. Why does it do that? I'm not exactly sure why. Oh, probably because I've imported other stuff and this thing imports torch directly. I almost wonder if I should write just like a little wrapper around that to like hide the stuff that I want. And then just a reminder that G is this, which is 9 plus 5 plus 1, which is 15. Okay, cool. So that makes sense to me. So this grabs 1. So there's our trace function. So that was cool. And we should be able to convert it back to a list, probably just with like maybe as list. So is there an as list? There's a as value. Oh, interesting. So I wonder if we can take as value. So let's do homing pigeon trace G and then as value and see what that does. So as okay, so we need to specialize as value to float, and then we're good to go. Okay, so so pull a value from a tensor. What happens if it's like the whole thing? 1. It just gets the first one? I find that a little odd, but like it just gets the first element in there. So that's actually fine. If you do like a complete reduction of whatever you're trying to do and then pull the value out, that's probably good enough. So this is like pull the first value from the tensor. Useful when doing reductions. Okay. Pearly Mo. That's an awesome name, first of all. Thank you so much for the follow. Appreciate it. Yeah, that was a huge raid from Raphael. I really appreciate that. People should go check out Raphael's chat for sure. Raphael Uba. No, what? What? Why? How do I? Why are you doing this to me? All right. Quick shout out one more time. Twitch TV / Let me make sure. There we go. Go check out Raphael. He's doing Jai.
I think I've actually seen Raphael before, but I could also be confusing him with someone else that does Jai, because I've only seen like 2 people do Jai on Twitch, so maybe 3 now. There we go. Okay, so we did that. Neat. Next, we talked about traces. Oh, I didn't actually finish this code. Gosh, I am distracted. So, get trace to value. So we're going to take a tensor and we're going to convert that to a float in our case, because we're just using floats. So trace to value is going to be trace after some. Oh, we already, like, it's really just as value. Like that. Cool. And then we could just use this. So trace to value G is 15. Nice. All right. Now we can keep writing. Okay, so we did matrix multiplication. Oh, I forgot to like look at that. So let's quickly go back to that because we got kind of distracted with this piece. So let's do like 2 examples of matrix multiplication by hand, and then go from there. So here we go. So this was the example we were just looking at. So 1, 3, 2, 4. Map mul 6, 0, 2, -1. Okay, so this is going to equal like what we'll call C1, 1, C 2, 1. C1, 2, C2, 2. Just so I can like pull this out. So C1, 1 is going to be, it's hard for me to draw this, but it's going to be the sum of this row multiplied with this column. Okay, so it's basically 1 times 6 plus 2 times 2. Okay, so that's 10, right? And then C21 is this row multiplied by that column. So 0, right, 1 times 0, and then 2 times -1. So that's just -2. I'm not going to do all the math if I don't have to. I'll try and go quick. And then C1, 2 is going to be this bottom row multiplied by the first column. I'm just going to take the number because I'm feeling particularly lazy. And then C2, 2 will be bottom row, right column, which is just -4 apparently. So that's like how you do matrix math. I like when I draw it or when I write it on a piece of like paper, I do this often. So it's like this row and then, this row, and like I just kind of like move my left finger over the rows and my right finger over the columns, and then that's how helps me do that. So I don't know if that helps you, then great. Also, one thing to note is that this is not it's commutative, not commutative. So you can't flip these arguments and it be the same thing. So E is not necessarily equal to F. And in this case, it's definitely not equal to F. So if we just look at E and F, there's E and F. So they're not equal, as you can see. Okay, cool. So that's one example of matrix multiplication and how we do it in TensorFlow. So we're making progress. Okay. Okay, so now there's some nice discussion about like how to think about matrix multiplication and a bit about shapes and stuff. So let's draw some pictures. So if we had a
matrix like this of k columns and n rows, matrix like this of k rows and m columns, the resulting dimension of this multiplied together always going to be n rows and m columns. So this is like one thing to note is that k always has to be equal to, like, these things have to be equal. Doesn't really make sense to write k equals k, but you need to have the same number of columns in the first matrix and rows in the second matrix. Otherwise, you can't do matrix multiplication. Okay, so there's a note about that. Matrix vector product. I wonder if we have to use matmul here. Anyway, so A times A is going to be B, and BI is equal to sum K, I, A, K, A, right? So we could draw this as a picture because the K on the right side is just 1. So you have like, let me just, the matrix we've been using. So 1, 2, 4 like this, and let's say we had this as 1 and 2. This will be, wait, which ones have to be equal? So this is not a row, it's a column. Otherwise, K isn't equal, right? So this dimension has to be equal to this dimension. That's the K's. So this resulting matrix will end up being K by M, which is just 1. So it has to be like a column vector, like that. I'm going to stumble over terminology for a while because, again, I haven't done it in a while. But again, you can think about this like this is, it's this times this, and then this times this, and you just sum them together. And I would guess that by default, matmul is smart enough to figure this out. So let's see. If we just take like H, which will be a tensor, and we want it to be a vector, so it's just going to be as tensor at float, like that, and then like 1 and 2. Is there an example in the book? There is not. So we'll just do 1, 2 like this. And what we want to do is reload this and then matmul A with H. So it should be 1 times 1, 2 times 2. It doesn't look right. Oh, yeah, duh. 1 times 1 is 1. 2 times 2 is 4. That's 5. So 5 would go here, right? And then that's 11. Okay, cool. I'm just being a doofus. So here we go. That would be 3 times 1, 4 times 2. 8 plus 3. Okay, so cool. By default, single dimension tensors are rows. Can we transpose H? Transpose H. Dim. Couldn't match dim. Why do we need dim with transpose? Transpose? Probably this one. Dim O. Dim 1. The first dimension to be transposed.
Okay. So it's going to be 0, 1x for the default, I guess. So dim 0, dim. Maybe I just need dim 0? I'm confused. Dim 1 h? Oh boy. Couldn't match expected type dim with actual type tensor in the first argument. What is this thing? Transpose. Dim tensor to tensor. So transpose dim 0, dim 1, h. Index error. Okay. That looks right. So I don't really think that you can transpose a like a vector. I guess it must just like orient the vector in the direction that it wants to. And so like doing the transpose like this will not get you to the thing that I was expecting. So I think if we did diag h, well no, that doesn't work either. Because then it's just going to like give us back the same thing. But if we did this, then we would get Oh, right. I have to say diag dim 0 or something. What is it? But that's just going to put it there, and that's not really what I'm trying to do. So, anyway, it's not that important, but I was just thinking about it. Okay, so there's that. All right, let's see. So, okay, so whenever we see an equation like the last one, which is this right here, in which a double indexed quantity and a single indexed quantity are summed over one index, we can view this as a matrix vector product. The summation goes over the second index of the matrix if the multiplication is capital A, lowercase a, with a column vector A. If the dimension of A is n and lowercase a, and A is dimension m comma n, then B has dimension m. Special case is when A has the dimension m equals 1, which gives a scalar for AA. That makes sense. So if m equals n, then the matrix A transforms a vector. The matrix A transforms a vector A. Okay. Okay, so the vector B equals matrix A vector A is another vector in the same plane with different length and orientation, and we may refer to A as an operator because A transforms vector A into vector B. We also call B equals a transformation. Okay, so let me write some of that down so that it's hopefully more clear. So B equals A can be thought of as an operator. We're going to talk about operators more hopefully next time, but yeah, we probably won't get to it today. So it's an operator. An operator, for some reason I want to keep writing apparator. An operator transforms an input. How do I want to write this? Okay. Um, it says also from the rules of matrix multiplication, one finds that for two vectors, the two vectors x and y, so here x is a vector and c is a constant. Um, okay, so these are the same things. So yeah, C1 and C2 are just numbers, whereas X and Y are vectors. Sometimes like depending on the context, like in physics, for example, you might see X written as this as well, which indicates that it's a vector, and that would make it easier to like visualize this. We could also use that cat notation from earlier and write like A C1 at X C2 at whoops cat Y, which maybe makes it more clear that oh well it's or something. But it's a little harder to write. So and like I think it's pretty or it's typically understood that C is something like a constant. So hopefully that's helpful. Okay. So there's that. Okay, so it says that the transformation so B equals a linear. The components B sub I B sub I of the transform B are functions of the components. Sorry, hard for me to read this from this far away. Where'd it go? Are functions. So, okay. B sub I. Oh, I think I went to the next page. Vector B are functions of the components A K of the original vector. I don't know what this means yet. What does this mean? Let's call the function f. We're okay calling functions f. Matrix multiplication function E equals A, and B sub I is equal to f of A1, A2, okay. And this is equal to this. Therefore, f is a linear function of A sub k. That is, no higher powers of A sub k, no products of A sub k with another A sub I, no square roots or nonlinear operations occur. If function f is not linear,
then so if f is non-linear, then A is not generally equal to C1AX C2AY. Okay. These kinds of things usually confuse me and have always confused me because I guess I don't understand often why we would rewrite this as some function of its components. But I think that ends up being useful later on, and I just like often get confused when these. So, okay. Let's just keep going. Hopefully there will be more obvious examples here in the future. All right. So B2, special types of matrices and operations. So we say like A is diagonal when like non-zero entries along the diagonal. So this is a diagonal matrix 3 0 0 0 0 0 1. And we some people will write this like pictorially. I need like space as something like this, where it's like you're saying that like all the values are along the diagonal. For proofs, likely, yeah. In proofs, all they do is syntax transformations until it becomes equal to definitions. Yeah, it like I think that when we get to cases with actual like functions of vectors and things, it will become a lot more clear. So that's a diagonal matrix. There's also a unit matrix, which is diagonal, and all values are 1. 1. So we might say like 1 sub 3 is a unit matrix. You could also maybe see that written like this. And then that would be like 1, 1, 1, like this. That's a unit matrix. Okay. Then we have a triangular matrix. Triangular. This is where either non-zero values below or above the diagonal. Values above or below diagonal. That, and we could see, for example, this is an A, like U. I can't remember if they use like upper syntax like this, but I think it's like that. So this would be an example of an upper 3, 7, minus 4, 0, 6, 0, 0, 1. Okay, so this is like an upper triangular matrix. If we wanted to turn this into A sub L, like A lower, we could just take A U and then transpose that. So then we'll talk about transpose next. So a transpose basically swaps indices. So if we had Aij and we wanted to take its matrix transpose, that would be the same as Aj sub I. Like that. So example A equals, say,
2, 6, and then we say transpose would be now 1. So basically, these, I don't know how to draw it, but this is always going to come up into the right corner. So 1, 3, 5, 2, 4, 6 would be the value. This arrow might be confusing, but that's basically the idea. Is like you're taking this matrix and then flipping it that. If you've never done transposes before. So like if we had a vector, like a column vector, so like 1, 2, a transpose would technically be a row matrix or a row vector like that. I think often the codes that we're going to use to do this stuff don't distinguish the difference between column and row vectors, excuse me. But that's okay. Okay, so a symmetric matrix has A transpose equals A. So you can flip it over its diagonal and it stays the same. Okay, and then, so this is actually one thing that the library doesn't support yet. So we're going to have to deal with this at some point, but we don't have to deal with it now, is complex matrices and Hermitian matrix. So if we had a complex matrix, a Hermitian is the following. So A J A J I star. So the star is a complex conjugate. If you've never dealt with this, I don't know if you can do this if complex numbers in Haskell have this. I'm actually genuinely curious right now. I just do. Oh, right. So if we had a complex number, complex numbers, conjugate. Okay, so there is like a conjugate function. So this will just flip the okay, so let me just like show an example because that's probably going to be easier. So if we had import data complex, and then we say like A equals, I actually don't know how to make one of these things. How do I make one? Okay, so I'm guessing the imaginary component is on the right, I would assume. So like if we do 1 plus 2, this means, well, we can just check. So if we do real A, how do we get the real part? Real part A should be 1, and imag part, which is the imaginary part, is 2. Okay, so good. And then if we take the conjugate of A, and then we look at the imaginary part, it should be negative. Right? And if we look at yeah, we could draw it on a plane. I haven't thought about that in a while. And if we look at the real part, like it would be like this. So on a plane, so let's draw like this. So this is real. This is imaginary. This is like a positive component, negative component. And then let's say this is 1, 1. And then this vector would basically be a complex number that's like 1 plus 1I. And if we wanted to take the conjugate of that number, which we'll just use this star to indicate its conjugate, we basically just flip it along the diagonal. So this becomes -1. This is going to call this A. This A star. -1. You don't really have to write the 1, but that's essentially what the conjugate is. This mostly readable? Hopefully. And obviously you can have negative real numbers. I just avoided that to simplify the picture. Now, one thing to note is that Hasktorch doesn't currently support complex numbers. So we'll have to kind of deal with that as we go. One thing that we could do is just create like a type and then lift all of these things over those types. So if we do like matrix multiplication, it has to be like very special, obviously. But maybe we'll just work on adding imaginary numbers to Hasktorch at some point in the future. Okay, so hopefully that was mostly like readable. Okay, so real symmetric matrix, because it doesn't have an imaginary number, it's always Hermitian, right? So real symmetric matrix is always Hermitian because the complex conjugate doesn't change the real number, right? So like you could say, let's say a real number is something like 1 plus 0j. So if I take the conjugate of the 0 here, nothing will change. So r star just is 1 plus 0j always. So any real symmetric matrix is Hermitian by default. Okay. Hermitian transpose. So what I wrote earlier, I think, was A transpose star. You could also write this as A dagger. And I find the dagger kind of hard to write on a piece of paper. But essentially what I've been doing is I do it like a squiggle and a dash. Because I can't really write. It's really not a good one. I need to find a better way to write the dagger. Like dagger like that. Maybe that's better. So it's not a plus sign, it's like a dagger is what it's supposed to be. It's very hard to draw to me, but you would pronounce this literally a dagger, and that's the Hermitian transpose. Okay. So like again, if A is real, if this is a real matrix, then a dagger is the same as a transpose. Okay. This only changes the world when we're talking about complex numbers. Okay. So the adjoint, the column vector A, so now we could write A equals A. This is where the ket notation becomes useful. Is the complex conjugate of the corresponding row vector. It's denoted by A dagger, or alternatively, the cat, or sorry, the bra. So if we say this is equal to 1, 2 minus I, 3 plus 2I, and we want to take a dagger, this is the same as the cat. Sorry, the bra. That's the cat. I keep saying them backwards. And then this just becomes a row vector. 2 plus I, 3 minus 2I, like that. Okay, so that's what this notation means. Can't draw the dagger at all. Very hard. Okay, so inverse. Inverse is noted a to the -1. Find for square matrices. And so a minus 1 is equal to a minus 1a, which is equal to 1. And this is 1 as in like a unit matrix, not the number 1. Cool. Remember that for non-square matrices, the dimension of a matrix can be multiplied with a from the left or the right is different, right? For non-square. So actually, let me draw this right in the center. Okay, so if we want to multiply from the left, so matmul from left, we need to match k. So we need to have, this is 2 by 3. So we need to match, sorry, which one do we? Yeah, we need to match this. So we need to have at least 3 columns. So this needs to be 3 by n. But if we want to match over here, this needs to be m by 2. Because, yeah. So the k needs to match. So this here needs to match. Number of rows on the right side, matmul from right. Right? And then this will generate 3 by n. Right? Correct. Or sorry, so 3 by 2. Right? Because this is our m in that case. And then this one will generate 2 by 2, I guess. Is that right? No. Wait, that's not right. Something's wrong here. It's 2 by n. And then this one is 2m by 2. There we go. Okay. I'll get it right eventually. Because this is k. This 2 is k. This is k. So it's m by n. That's m. That's n. 2n. M is the thing coming from the right. K is 2, so it's m by 3. Gosh, I always mess this up, like literally every single time. It should like be ingrained in my head by now, but it's not. So anyway, there we go. So for non-square matrices, one can either define a left inverse or a right inverse individually instead. Only one of them can exist. For a square matrix, the left and right inverses are identical. Here are some examples. I don't know how inverses work in Torch, so let's check it out. Excuse me. So let's try to invert G, if that's even a thing. Inverse. It is a thing. What does it take? Just a tensor. So what if we inverse G? Error. U33 is 0 singular. I don't really know what that means. Is this unitary? Do the inverses of A or B exist? Apparently they do. Okay, and then what if we do a non-square? Well, let's do one that exists. Well, supposedly this exists. So I don't know what this is going to do, though. Yeah, it just fails. Okay, so matrix inverse doesn't really behave the way we want it to, I guess. At some point, we're going to have to compute inverses. Out equals none. Okay, so computes the inverse of square matrix if it exists. There's a runtime error if the matrix is not invertible. Invertible, in this case, the inverse is unique. Float double. Okay, so consider using Torch-Linalge solve, if possible, for multiplying a matrix on the left by the inverse as the following. It's always preferred to use solve when possible, as it is faster and more numerically stable than computing the inverse explicitly. Okay, so see also solve. Okay, so right hand side. What is this at for? Consider using, if possible, for multiplying a matrix on the left by the inverse. So we're not, I guess I don't understand what this is doing. Do we have solve? And what's the shape of solve? Takes two tensors. Okay, so what if we try to solve I don't really know. I don't really understand what this is saying to me. It just needs to be the right shape, maybe? So what's the right shape? If we do this on the right-hand side, it just needs to be 2 by 3, right? Um, okay, so it doesn't really work. So inverses in PyTorch libtorch expect square inputs. So I think you have to use like some other linear algebra magic to compute inverses, I would guess, which is fine. So it says, in general, a matrix inverse is not so easy to calculate. We refer to the literature on how to do this. Powerful computer algorithms exist to compute inverses for large matrices numerically, and they scale about n cubed, I guess. Okay, so anyway, that's enough for inverses, I guess. Orthogonal. And orthogonal, I think I switched O and A. Orthogonal, like that. If real has a property ATA equals AT equals 1. And AT equals A1, right? Because A minus 1, right? Its transpose is its inverse if it's orthogonal. Okay, so I think we need to stop here because it's like way later than it's supposed to be. But we'll come back to orthogonality next time. And I should have stopped a little while ago, but I was stuck or thinking. So we'll keep going next time and learn a bit more. I need to think about the inverses at some point. So on orthogonality section. So that's kind of the next thing that we need to do. And that's where we're at. I will see y'all later.